Well, clearance is clearance, Clarence. I say send it. So you bought a lathe, and let's be honest, you're not totally sure what to do with it. Now, 7 years from now, this is going to happen, but you're not there yet. You've got this thing, you're excited about it. What you need is something fun to build. And more than that, something that you couldn't build before you found out you have a magnetic personality and cast iron started following you home. So we are going to build something cool today using only your lathe. It's what I'm going to call an air engine. I mean, you could call it a steam engine, but not everybody likes steam engines because they're stupid and old, I guess. But this thing will run on air, it'll run on, you could run it on the CO2 tank from your welder, whatever, any kind of compressed gas it'll run on, and it'll run on steam. So even if you're not into steam engines, this is the project for you because there is nothing like the satisfaction of seeing an intricate little machine of any type that you built with your lathe and just your hands, and you couldn't do that before you bought that expensive machine. So we're going to do that right now. Let's go. Here's the engine we're going to build. It's a classic bar stock wobbler. It's the first engine that you should build if you're at all interested in building engines, steam or internal combustion or anything else, because this very simple form of engine has very few moving parts. It's extremely forgiving on tolerances, and it'll give you a lot of skills that you're going to need to build more sophisticated types of engines. I want to give a quick shout out to stevesworkshop.co.uk. The very first engine that I ever built in my machining hobby was his design for a bar stock wobbler, and it's a lovely one. This design is inspired by him, and I wanted to shout that out because he got me started on this road, and I would like to do the same for your journey. What I've done is simplified the concept of a bar stock wobbler as far as I feel like I could. I reduced the part count as much as I could, and I reduced the overall complexity, tried to make it as easy to build as possible. I wanted this to be the first real thing that you build on your lathe after you've watched my lathe skills playlist and made some round things into smaller round things. Now, the full drawings for this engine are going to be available to everybody. Normally my drawings are reserved for patrons, but I want this to encourage more people to build cool stuff with their lathes, so all the drawings for this are going to be linked in the doobly-doo for every video in this series. And if you appreciate that, then yeah, throw me some bucks on Patreon if you like, but the drawings are free. If we take a closer look at the top area of the cylinder, you can see how a wobbler works. As the engine rotates, the valve, if you will, which is just a hole on the end of the cylinder, aligns alternately with one hole in the frame and the other hole in the frame. The left-hand hole is the exhaust and the right-hand one is the intake. So the wobbling of the cylinder creates the valve effectively just by moving back and forth. It's a very elegant and simple design. Not a very efficient one, but it is very, very simple and easy to build. This is a real engine design. These were used in things like small steam launches, a couple of similar marine applications where simplicity was desired. It's not an efficient design. It's wasting a lot of energy swinging the mass of the cylinder back and forth, and it's never going to seal very well. We're asking a lot of that surface between the frame and the swinging cylinder to seal against the gas pressure. And there's a limit to how well it can do that and still be able to swing freely. So it's going to waste a lot of air or steam. Not very efficient, but for a model engine and for your first build, efficiency doesn't really matter. We just want it to run, and this thing will run. I've tried to design every component to use easy-to-obtain materials in common dimensions, and it should be buildable on just about any lathe. I think even the Chinese 7x14 mini lathes that are very popular. I don't have one of those, but all the parts here are small enough that you should be able to build it on one of those. Here are all the materials you'll need. We've got some steel for the crankshaft and the flywheel, and a bunch of brass. This is for the cylinder. Then we've got a chunk for the piston, and this rectangular bar stock is for the frame, and then an optional little hex piece for the air fitting. This could also be round bar. You could make it out of the same bar as the piston if you wanted. And then on the top left there, we've got some drill rod, and these are for the crankshaft and a couple of pins and other rotating pieces. Using drill rod, or what the Brits would call silver steel, is a great shortcut for beginners making small engines because it's extremely accurately finished and dimensioned. If you buy precision ground drill rod, it'll be within a few tenths of exactly the right dimension, and it's got a polished finish on it, so it runs great in brass bearings, which is what we're going to be using here. The frame is made of brass because it's also acting as its own bearings to get the part count as low as possible. Again, because the pedants are going to complain, brass is not the best bearing material, but this is a model engine that's going to run maybe a few hours in its entire life. So again, the focus is on making it easy to build. We're going to get started with making that frame now. This is the piece of square bar. It's a standard 3/4 by 3/8 dimension. Should be easily obtainable at any steel yard or online if you prefer. Now it's over length, it's about 6 inches long, and we only need 4 inches for the frame. And that extra length is going to assist in fixturing. Because we're doing this lathe only, we need to do all of our milling on the lathe as well. And that means it's faceplate time. So I'm going to fixture this on the faceplate, and we're going to mill one surface of this frame flat. We need one surface to be flat because, as I said, that is the valve's sealing surface with the cylinder, so we need it to be as nice as possible. Now, I will say this is optional. I have built this engine without milling this surface, and it also, frankly, runs just fine. But it's a good excuse to show you some milling techniques on the lathe. The extra length is there to allow us to clamp the ends of it and then mill the center area flat with the cross slide on the lathe. You'll see how this works in a second. Now, lathe face plates are easiest to do on the bench, as you saw there, and then bring the whole thing over rather than trying to do all this with the parts hanging in space and falling and so on. Gravity's not your friend there. I think a lot of beginners are a bit afraid of faceplate setups or are just unfamiliar with them because you don't see them very often nowadays. Chucks are a relatively modern invention in the lifespan of the lathe. However, faceplates are kind of the OG work holding. Aside from working between centers, pretty much everything used to be fixtured on the faceplate. And it's a critical skill if you're going to do lathe-only work as we're doing here. Now, you always got to check your clearances on the faceplate. You'll find out how little clearance you actually have around the front of your carriage as soon as you start doing faceplate work. In this case, my clamps are going to hit, so I got to keep the carriage back a ways. You can often gain extra reach, sometimes the amount that you need, by swinging the compound around and sticking it out over the end of your carriage. And then if that isn't enough, you can also use tool stick out to get the reach that you need. That's sort of the last resort, but tool stick out can sometimes make the difference. However, that wasn't going to work for me. It was too far away still, so I went and rotated the clamps sideways, which brought them further into the center of the faceplate, which gives me the clearance around the front of my carriage. Now, to do this, I needed to drill and tap some new holes in my faceplate. First rule of a lathe-only lifestyle is do not be precious about modifying your faceplate. That is what it's for. Drill and tap holes anywhere you need to make it easier to fixture things. In this case, by swinging my clamps sideways, I can now get all my tooling much closer to the work. However, faceplate setups will also show you all the sticky-outy bits that you didn't know your lathe had, such as this end stop bolt on the end of my compound that I never noticed before until now when I was checking clearances, and it's going to be in the way. Now, I could probably get away with this. That's not a huge amount of stick out for the light cuts that we're going to be doing on that tool, but I still wasn't happy with it and eventually arrived at the much simpler solution of simply bolting the part to the faceplate. Yeah, sometimes you got to try all the silly stuff before you get to the obvious answer. And by that I mean I was just showing you all of that other stuff so you could see some techniques of clamping and modifying your faceplate and so on. It was definitely not because I hadn't thought of this yet. Shut up. Anyway, as you can see, we now have all the clearance we need with very little tool stick out, and we can get in there and face that length of the bar in between the bolt heads. So away we go. This is just going to be a very light, minimal material removal kind of cleanup. We just want to make it nice and flat. If you've looked at the drawings for this project, they show that the bar stock that we have is actually already the nominal size for the frame, but none of the dimensions on the frame are particularly critical, so we can remove material here and there just to make it look nice, or in this case, to make a better valve surface, and it's not going to hurt anything. I'll speed this up because long facing cuts like this are pretty slow. This is where power crossfeed on your lathe is a very nice thing to have. And just like that, we've got a very nice flat milled surface on our frame. Looking good. We could certainly stop here because the other side of the frame doesn't need to be machined. However, just for giggles, I am going to machine the other side just to make it look nice. Now, note that this is not guaranteed to create a parallel surface to the one we just made, because as I flip the bar over and clamp it to the faceplate, we're still clamping on the unmachined areas at the end of the bars. So it'll be pretty parallel, but to guarantee perfect parallelism, you would want the machined face that we just made to be fully registering against the faceplate itself. But if you do need that to be the case for some other project, I'll show you how to do that in a minute. But for now, we just want this face to look nice, and so I'm just doing a light cleanup cut. Don't really care if it's parallel to the other one. Shiny. Now this is just one way to do milling on the lathe. We're going to talk about more methods in a minute, but you You can see that that worked really well for this particular part. Now we can cut the 4-inch chunk that we need out of the middle of the machined area. I'm actually cutting it over length because we still need to machine the ends and we want the overall length to be accurate. If you wanted to ensure maximum parallelism of those front and back faces, as I talked about, what you would do is start with a longer bar, machine one face using the technique I just showed, then cut off the ends like I'm doing here. Then you've still got excess length left. You can put new fixturing holes in, bolt it to the faceplate with your machined face up against the faceplate, machine it again, and then cut off that extra excess and end up back where we are now, and your faces would be parallel. But that does cost extra material and time, and again, wasn't necessary here. Now to machine the ends, you can see I've got the 4-jaw chuck in there. This is a pretty straightforward 4-jaw chuck setup to machine those ends square. We are assuming that the jaws are going to hold the part straight in the chuck, which they usually do, but if your chuck is worn out or really cheap, it might not, so you may want to run an indicator on there and make sure it's sitting coaxial with the axis of the lathe to make sure that the end that we cut here is square to the sides. I'm going to check it quick with an indicator. I'm not actually going to dial it in because it doesn't need to be for a facing cut, but I don't want it to be running too far out because the lathe will vibrate and it'll scare the cat, and we don't want that. In this case, it's already within like 10,000ths, so that's fine. And at this point, it's just a case of making a light cleanup cut on this end, and then we can proceed. I'll take a moment to note here that you could actually do that facing cut that we did on the long sides in a 4-jaw chuck as well, if your 4-jaw chuck is big enough. However, I didn't want to assume that you have a 4-jaw chuck big enough to do that. I think mine might be, it would be close. But if you're on, for example, a 7x14 mini lathe, it probably isn't, so I want to show you other options. There are no small lathes, only small machinists. Now I can flip it around and we're going to face the other end. We're trying to get down to an overall length that's specified in the drawing. So the first step, as with anything in the lathe, is to clean up both ends. And once we have two cleaned up ends, we can take a valid measurement and see how much we have to remove to get down to the correct length. This is why you got to leave lots of extra material over on the bandsaw so you have room to face both ends, measure, and then face down the rest of the way to get to the exact measurement. So these final couple of cuts are done in however many passes you feel are necessary to get down to the final length that the calipers told you need to get to. And just like that, we are dead nuts on 4 inches. Looking good. At this point, we've got the two big faces and the two ends nicely machined, but what about these long edges? Well, my original plan was to just not care about them and put them on the Scotch-Brite later. However, it occurred to me that this is another good excuse to show you some more milling techniques. So let's flip the script and I'll show you the other category of milling techniques on the lathe, which is to put the cutter in the spindle and fixture the work over here on the cross slide. Now to do this, you really want some kind of T-slots or other fixturing methods for your cross slide. If you're buying a lathe, make sure it's got something like this. You're going to need them. And one easy way then is to put an angle plate right on your cross slide and fixture the part like that. And you can run that right across that milling cutter. Of course, that doesn't give you any height or y-axis adjustment of the part, but if you're just making a cut on a thin part like we're doing, then this works just fine. If you do need that y adjustment, then it's time for something called a lathe milling attachment. Here's an old palm grin, but they actually still make these things for modern Chinese lathes. So if you're interested, you can buy them, and they are also a popular project that people make for their lathes. As you can see, it's essentially a glorified angle plate, but it has height adjustment on it, and it's got a vise integrated into it to make work holding easier. And some of them also have, like this one does, a fancy angle adjustment as well to give you some more options. You don't see these as much today because hobby milling machines have become so cheap and plentiful, but for the first 100 years or so of the model engineering hobby, these things were de rigueur. Everybody had one. All the usual suspects made a version of it for their lathe. Myford, Atlas, Logan, they all made one, and you were pretty much going to have one because nobody had their own milling machines in those days. Same as today, though, if you are not going to have a milling machine for whatever reason, and you do plan to do a lot of milling, these things are a very worthwhile thing to acquire or make. For very occasional horizontal milling, however, there is another option. You do already have a somewhat height adjustable mounting system on your cross slide. What else needs to be mounted on your cross slide and be height adjustable? Your lathe tools. So the lathe tool holders, in fact, with their little built-in height adjustment, can make quite a handy little milling fixture for your lathe. I'll show you how that works right now. I'm going to dial that in. Of course, it has to be nice and square to the spindle to make sure we don't create a tapered part. So I'm going to indicate in the back of that because it's going to be my reference. And I can slide my part in here like this, protect from the set screws with some shim stock, clamp it down, and presto, we've got a horizontal milling attachment on our cross slide. Obviously, the capacity is limited by the size of your tool holders, but this actually works more often than you would think. I have actually done this multiple times. It's pretty often that you're making small things in model engineering and they will fit in your tool holders. Now here is the problem, however. You don't have a lot of range of travel. As you can see, I've only managed to reach a third of my part in this case. And again, sometimes you can manipulate the compound to give you a little extra travel, but generally speaking, you're not going to have much travel because the tool post is biased to the outside of the cross slide. If you had an angle plate or a milling attachment, it would be way out here in the middle of the cross slide and you'd have the full range of travel of your cross slide. There's still a takeaway hiding in here though, and that's that even with a milling attachment, your capacity is going to be limited by the travel of your cross slide. And on hobby lathes, it's often pretty small. Like on mine, I think it's 3 inches. But you can flip the part end for end to double that reach effectively, do multiple setups for a single cut. So there are some ways around it, but ultimately this is why the faceplate is often the better option, because what the faceplate is doing effectively is using rotation as your y-axis. That's part of what makes lathes so clever. So get comfortable with your faceplate. In my case, I'm going to go back to plan A, which is to not care about those edges. Over then to the lathe's best friend if you're not going to have a mill, and that is the surface plate. If you don't have a mill with the benefit of its hand wheels and or DRO for locating features on your part, then getting comfortable and competent with layout and surface plate work is critical. So let's get the layout die on there, and I am using layout die, not Sharpie. Don't use Sharpie if you're going to do serious layout. It's fine for 1 or 2 cuts, but it isn't durable enough to survive multiple operations. So I'm going to run a center line down the middle of my frame, and then I'm going to turn the part on end, which is why we machined the ends before doing this, and I'm going to mark the height of all of the holes that we need to put into this part. There's the crankshaft and the cylinder's pivot point, and then the 2 valve holes. Now I'm going to very carefully center punch these. The accuracy of the rest of our work depends largely on how good these center punches are, so take your time and do it well. A lot of people like an optical center punch for this. I'm not a huge fan of them myself. I have better luck doing it by feel, but if you get a punch you don't like, remember you can always move it, punch it at an angle, and then punch it again straight down until you're happy with it. There's our punches, looking good. Now for the crankshaft hole and the cylinder pivot, those need to be very square to the frame. So I'm going to do these on the lathe, again with the surface plate. However, the big surface plate is going to be a little bit clunky for this, so I'm actually going to use a little surface plate because it'll be quicker. This is just a shop-made one, and if your lathe didn't come with a faceplate, you can certainly make one the same way. It's literally just a disc with a bar stuck in the back of it, and it mounts in the 4-jaw chuck. And every time I use this thing, I take a light skim cut on the front of it. It's not dialed in, doesn't matter, we're just facing. But because there's a lot of variables in the chuck jaws and so on, it doesn't necessarily get held square in the chuck. So taking a quick facing cut guarantees that front surface is perfectly square to the lathe. And now I can clamp my part in there and I can dial in the first of the center punches. My favorite technique for this is to suspend the dead center between the punch mark and the live center, and then dial in the dead center. And by holding the faceplate in the 4-jaw chuck like this, it makes it very easy to dial in. We don't have to tap anything around like you do on the faceplate. Then from here, it's a standard drilling operation on the lathe. In this case, I'm going to choose to center drill, and then I'll do a pilot drill, and then I'll finish with a reamer to get an accurate dimension and geometry on the hole. You could also bore it before reaming if you want to be extra fancy, if you have a small enough boring bar. The boring bar would ensure perfect positioning of the hole, but honestly, that isn't that important for this little engine. The reamer is going to make sure that the crankshaft runs nicely in the hole, but the boring bar really isn't necessary. This is a very reamer-friendly engine. You can pretty much do everything with reaming. Speaking of which, here comes the reamer. This is the nominal size reamer of the drill rod that is going to be the crankshaft. More on that in a second. You will notice that the lathe is wobbling a little bit because of the eccentric mass, but it's not a big deal. Everything's wobbling together, so it doesn't affect the accuracy of the cuts. Now I will test fit with the chunk of drill rod that's going to become the crankshaft, and as we can see, it's a very snug fit in there. It's kind of a gauge pin fit, which is technically what's supposed to happen because we reamed it to the nominal size of the drill rod, which is precision ground, to that same nominal size. That means it's time for the model engineer's best friend, over-under reamer pairs. I've got a 251 reamer that's 1 thou over 1/4, and I will ream it out to that. The reason I don't start with this reamer is because drill rod has a tolerance on it, so it might be a few tenths undersize, and the first reamer might have cut a few tenths over if something wasn't perfect about the setup or the reamer itself, and sometimes you end up with a good running fit anyway, but in this case it was too tight, so oversize ream it, and now it's a perfect running fit. Then I loosen up my clamps and I slide the next hole, which is the cylinder pivot, over to, again, just eyeballing it in the center of the faceplate, dial it in, drill it, ream it, all the same procedure. I should point out, because I haven't mentioned it, the layout was all done on the side opposite the valve sealing surface, because I want that valve sealing surface referenced on the faceplate to make sure that these holes are all as square as possible to that valve surface. But those are all the holes that need to be square as possible to the valve, so I'll take that down out of that setup now. We still have the 2 valve holes to do, but they don't need to be so perfectly square, so I'll do those on the drill press, which will be much quicker and easier. If you're going to live without a milling machine, I do recommend you have a drill press. It's a pretty essential piece of equipment. I mean, you can drill just about anything on your lathe using these techniques that I've shown, but boy, it's a lot of work, and you really want a drill press anyway. Even if you're a woodworker, you want a drill press, right? I've lined that up using a center finder and my float lock vise in concert, but there's other ways to do that. This doesn't have to be super perfect because we're using a thin, flexible drill, and I'm not center drilling here. I'm going directly to the drill, and it's going to find that punch mark and flex as needed to stay on target. We do want the position of these holes to be fairly accurate, so this is actually more accurate than center drilling would be on the drill press. Because if my punch mark alignment wasn't perfect, the center drill would actually damage the position that we established with the punch mark. So in this case, it's better to let the drill bend and do its work. That first one went only halfway through the frame. It's the intake, and the exhaust port goes all the way through, and there's our 2 holes. Looking good. Back to the surface plate one more time. There's a couple of holes on the ends of the frame. There's the air intake at the top, so that's an easy setup again in the 4-jaw chuck, just a standard lathe drilling operation, dialing that in the same way, center drill, tap, and then there's also 2 threaded holes on the bottom, which were done the same way, and those are for mounting this frame to whatever you want to mount it to. We're done with the layout now. You can see it took a beating from the 4-jaw chuck setups, but it lasted 10 times longer than the Sharpie would have, I can tell you that. Diecam is good stuff for real layout. A little acetone bath gets rid of it. Again, because someone's going to complain, Sharpie for layout works just fine for 1 or 2 cuts if you don't have a very demanding situation, but if you want your layout to survive over multiple setups and multiple operations, you really want to use Diecam. Oh, and yeah, that aforementioned Scotch brighting of the edges, just to make them look nice. There's nothing critical about the flatness or squareness or dimension of the edges of the frame. And there it is. There's our very fancy stick, but it's a fancy stick made entirely on the lathe. And we learned a whole lot about milling on the lathe, I hope. Anyway, I hope this was helpful for you. And we've got a great start on our little engine. Obviously, we've got more parts to make, but we've got an awesome start. And we're going to be continuing this series, so stay tuned for the rest of the parts on this engine, and it's going to be a lot of fun. Thank you so much for watching. Thanks to my patrons for making all this happen, and I'll see you next time.